Am I audible, sir?
Yeah, you're audible.
Can you please wait,
Yes, sir.
Savitoj? Just 5 minutes.
Yes, sir. Sure.
Just five minutes. Okay, Savitoj, you can start, I think. Savitoj.
Can we start, sir?
To the schedule, Savitoj. So let us start.
Okay.
That's the advantage of online platform meeting. So let us stick to the deadline. I mean, the timings. Let us start, Savitoj.
Okay, sir. Good afternoon, everyone. For this session of today's workshop, I'm very pleased to welcome our speaker, Dr. Sagar Telrande from MRF Tires. He completed his undergrad in mechanical engineering in Nagpur University and then his MTech in NIT Surat, and then achieved his doctorate degree from IIT Bombay in 2017. His professional achievements include a patent on method for improved sheet formability of hardenable metallic alloys, along with several publications in reputed conference proceedings. With an expertise in machining, finite element method, and microstructural characterization, he has been instrumental in research and development in these areas of research. The topic of his today's presentation is surface modification of TI6AL4V to improve its machinability for aerospace applications, and he will be sharing his expert opinions on the same. Please, sir. Sagar, sir, you can continue, sir.
Thank you, Savitoj. Thank you. Am I audible to all of you?
Can you make him co-host, Savitoj? Yeah, he's co-host. Are you able to share screen, Sagar?
Sure.
Yeah.
Yeah.
Yes, sir.
Okay. Yeah.
Just can mute,
You
please.
can see my screen. Am I audible?
Yeah, you can bit increase the voice.
Okay. Okay. Just a minute. Yeah. Now is it okay?
No.
Uh, is it okay now? Srinivasan, am I audible?
Very low volume.
Okay.
Very
So.
low volume.
Okay.
Yeah, I think you don't need this earphone.
Okay. Fine. I will connect with.
Just
Yeah, now it's better.
yeah, now it's better, right? Okay, fine.
Better, much better.
Okay, I will go ahead with this then.
Yeah.
Fine. Yeah. So should I start?
Yeah. Please.
Okay.
Yeah.
Good afternoon, everyone. So I'm Sagar, and thanks for the brief and nice introduction. So let's go ahead with the topic. It's a subsurface modification and its effect on machining of die 6 for alloy. So this is nothing but overall my work in the PhD, and that has been concerned with the advancement in machining, well, especially the titanium machining. Here we'll talk about the microstructural aspects of titanium, how it affects the machining, how the modification in subsurface will affect the machining. Okay. Okay, so this is my brief review. Okay, so I think most of the introduction has been covered up. And currently I am in MRF R&D. So I'll be dealing with establishing a state-of-art lab facilities over there. And I'm incorporating the static and dynamic test simulation in collaboration with the DS. Okay. Fine. So to start with the topic, let's see the application of titanium and its alloys in aerospace. So titanium alloys has been widely used in this sector, especially if you see in the landing gear. Many titanium alloys has been used till now, but currently TI 5553 is most widely used in engine parts like fan blades. Then there are many structural parts where titanium is used widely. And over the years, you can see their usage has been increased drastically from 1950s to 1980s to 2000, 2010s. Okay. So here, if you see any of the part that has been the major part has been processed through machining. If you go to check even even a billet, so the end usage of that billet will go forward with the machining, and there will be around 90% of machining operation going on either of the parts. So only 15% of the remaining part is going to have an end use in aerospace process. So you could see how important the machining process for aerospace as well as for biomedical application is. For biomedical also, in case of titanium, it's a non-reactive material, and well, many of the hip joints, knee joints are made by this material. So there also machining application comes hold good. Okay. Let's move ahead. So here we have seen why machining is important. So let's see its mechanism, especially in case of titanium machining. Why titanium machining is different from other metal machining. So you must have heard about the different kind of chips formation in case of machining. There is continuous chips, there are discontinuous chips, there is one other category known as segmented chips. So for many of the steel application in case of machining, these kind of segmented chips forms when you subject the machining process for high speed cutting. Whereas for titanium, whether you cut at high speed or at low speed, the segmented chips will form. Those are inherent segmented chips. And here, these are formed due to the shear band formation on the rake face. If you could see over here, this is the rake face, okay? And the conductivity of titanium is very low. So what happens over here is the frictional forces generate over here on the rake face, the heat gets entrapped over here because titanium has very low thermal conductivity. So here the localized shear band forms, and during machining what happens is the speed, the local speed in the shear direction and the local speed in the chip direction, those creates a gradient. And because of that gradients, you could see the segmented chip formation. And what happens due to this segmented chip formation is you will get higher force over here, reaction force here, over here, and low reaction force over here. So this kind of segmented chips will create higher and lower reaction forces, and that will create some local vibration on the cutting tool. So that local vibration will drastically affect this tool life. So most for the times you could have seen the titanium machining, usually the cutting speeds are limited. We cannot go the cutting speed same as aluminum or same as different kinds of steels, keeping apart the high strength steels. Okay, so that is the main reason that why titanium machining is difficult. So many of the people have tried to address this issue, like they tried to modify the operating parameters, use of coolants, use of modifying the tool geometry and all those things. So like modifying operating parameters such as cutting speed, feed, uncut chip thickness, that means the depth of cut, coolants. So people have used solid lubricants, soluble lubricants, even liquid nitrogen. Then the conventional way another conventional way to improve machinability is to give different tool materials, try on different coatings. Tool materials could consist of carbide tools, then HSS is always there. Coatings people applied on the tool to make it more strengthened. Then to change in tool geometries, like you can give the chip breaker, you can give the different rake angles, you can give the we can say different relief angles and all those things. Okay, so these are the conventional way people have tried over here. What we tried in our approach is going with targeting directly the segmentation of the chip. Yeah, so what we did initially, we gone forward with the as received material. I will explain you what these images are. We gone forward with the as received material, and we did its annealing at different temperature. Annealing is nothing but heating the material for few hours to get the uniform microstructure of that material at that temperature. So here you could see these are nothing but the EVSD scans, electron backscatter diffraction scans. So each and every okay, so each and every color over here shows a particular orientation at which the atoms has been arranged inside the grains. So these are the grains, and the black line shows its boundaries. Okay, so here you could see the annealing part has affected the grain size, its orientation quite a lot. Overall, till annealing at 900 degrees Celsius, there is no domination of a particular orientation you could see. But over here, when you anneal it at 925 degrees Celsius, you could see a completely different structure. That is because you are annealing it near to the transition temperature. So transition temperature is nothing but the temperature at which the main initial phase of the material gets changes to different phase. Let us say the Ti6 material, the titanium, is basically an hexagonal close pack structure material. So when it anneal at higher temperature beyond 1000 degrees Celsius, so it changes its structure from hexagonal close pack to body center cubic structure. So since it this annealing has been done very near to the transition temperature, that's why this kind of abrupt structure has coming up. So we'll see what are these structures and how this grain size has affected in machining. So what we did next time, we subjected this all material to machining. So here you could see I have plotted the cutting force with respect to time for every anneal conditions. And if you see closely, if you observe the anneal 625 degrees Celsius and anneal 925 degrees Celsius, there is a huge variation in cutting forces for higher anneal samples. Okay, that means here we could see the grain size has affected a machining. So why this cutting force variation is happening? Just the things which we have seen earlier because of the segmented chip formation. So this means that if you have a higher grain size sample, so the segment variation will be huge. That means maximum and minimum forces, there will be a huge variation. Well, that could affect the machinability. Although the cutting force, average cutting force values has lowered in this region, still the variation has been increased. Here you could see the average cutting force value is coming around 300 Newton, whereas here the average cutting force value is coming around 350 Newton. However, the variation has been reduced a lot. Okay, so any questions? Let's see till now.
Sagar, let us have the interactive session later. Let us
Okay, okay.
see presentation. This is
Sure,
how it is
sure.
organized.
Okay, okay, fine, fine. Yeah. So moving ahead, we did the subsurface analysis after machining also. Here you could see, so after machining, there is a finished surface forming up. So if you cut the cross section of that finished surface and see in the thickness direction, how the machinability how the machining process has disturbed the basic structure. So here you can see, because of machining, there is a local deformation has formed. That's why in EBSD we could not index these regions. This is the black regions. Okay, but here we could still see what different kinds of things has formed due to machining at the subsurface. So with as received and annual 725 degrees Celsius, we could not see much of those things because there are the highly distorted structure has formed. But here by this distorted structure, we could see how much is the machining affected zone. Means due to machining, how much distortion happened at subsurface level. Okay, so there you could see uh, at subsurface level, when you increase the grain size, okay, the effect, the depth of machine penetration has been reduced, okay, for every cutting speed. Yeah, and even after that, even the residual stresses has been reduced for the highest grain size sample. That we have seen means these residual stresses are directly proportional to the cutting forces. So we have seen that average cutting forces has reduced over here. Okay, that because predominantly here the grain size has been increased, and that has reduced the hardness of the sample, and because of which you get the lower average cutting forces. Although you get lower average cutting forces, but still you have higher variations in that cutting forces. Okay, so in a way we could say that increasing the grain size could increasing the grain size could lower the cutting force, means could lower the power consumptions also. Okay, however it could increase the variation on the cutting tool. Okay, and in case of titanium machining, the cost of machining derives by cutting tool predominantly. Okay, so these are the conclusion for from this area. I have two more areas to cover. So the average cutting force has been reduced. The compression twins were formed. So here in this region, if you see, these are nothing but the twin formations over here. Okay, so that means the grain orientation has been mirror image to each other. So between this grain and this grain, there are almost mirror images at some angle. Okay, those are nothing but the twins formation. Okay, yeah, and for highest annual sample, the deformation mechanism was switched from slip to twinning. Okay, slip phenomenon is nothing but when the dislocation movement happenings inside the grain, that is nothing but the slip phenomenon. Twin phenomenon, the one which I just told you. Okay, so both has contributed to the plastic deformation. Okay, yeah. So next part, I have gone through the surface modification with laser treatment. So what was the reason to do that is, I have seen at lower grain size, the cutting force variation was quite lower. So because of the grain straightening, this kind of mechanism happens inside in metallurgy. Inside, okay, if you see at the micro level, so we thought that okay, with laser surface modification, we can reduce the grain size even below to what we got at 620 degrees Celsius annual sample. So what we did, we took the cylindrical sample, we laser treated it. So we calculated the depth of penetration. Okay, and accordingly we decided what should be our laser parameters. So we should be able to machine the surface which has got microstructure modification. So that's why the here you could see when laser moves forward, okay, it affects its microstructure in the depth direction. So what happens, laser heating is nothing but the point source heating. So when high energy laser beam comes on this portion of the material, the whole other material acts as a sink. So what happens over here is there is a sudden thermal gradient formation. Okay, that means higher temperature to low temperature. This mechanism is similar to the quenching mechanism. So that's why you could see very fine grain structure forming at localized level. Okay, let's move ahead and see the results of this thing. Okay, yeah, so here you could see we with 3 different scanning speed we can achieve the different depth of penetration. Okay, so this is the laser treated sample. If you take the section of it, that's how you could see the penetration. Okay, and since as we move ahead on the sample with laser movement, okay, the depth of penetration increases. This is because we give some overlap after each movement. So here you could see this is nothing but in the helix pattern. So your sample is rotating, okay, at certain RPM, and then accordingly the feed has been provided to the laser treated sample. Then the feed is provided such that your sample the laser beam will have next laser beam will have overlap of about 70%. Okay, so that's why you could see the penetration depth increasing over the length of laser travel. So now what happens with this penetration? Okay, with this penetration, you could see the change in microstructure. So from here, this is the end of the yeah, this the portion. Okay, from here I took the laser scan. Okay, so from surface to center, the surface to center, the structure has been changed, and after certain depth, you could get the aqueous grains that is nothing but the original structure of the material. Okay, yeah, just give me a minute. Okay, let's move ahead with this. Yeah, so after that, I wanted to check what could be the hardness variation due to laser treatment. In all of the scanning speed, we could see there is an increment in hardness, and uh, and as we go near to the base structure, the hardness has been reduced. So this hardness is nothing but the hardness at the of the base material. Okay, so these are the micrographs. Here you could see this is the encircle region, and this encircle region is nothing but the penetration depth of laser that we have calculated optical through optical measurements. Okay, so at that encircle region, what is the microstructure? The microstructure is like this. So these are nothing but the these are nothing but the ACM images, scanning electron microscope images. So here you could see, these are the grains and these are the grain boundaries. So these boundaries everywhere has been affected due to the laser treatment. So initially the laser treatment affects the whole grain structure, but when it goes near to the base material, it affects only the grain boundaries. Okay, because the grain boundaries are nothing but the weakest section uh, inside the grain structure. Okay, that's why it has very high energy to shift. So these grain boundaries will try to go in the stabilize phase, and in between so since the laser treatment is not allowing to uh, the time to go into the stabilized state, so it has been restricted over here itself. Okay, yeah, after that I have seen whether any new phase has been formed on that because of laser treatment. So I had did the XRD analysis, X-ray diffraction analysis. So here we could see this is the structure of base metal, and this is the 2 theta graph of base metal, and this is the 2 theta graph of laser affected zone. That is nothing but here the new peak, the peaks over here shows the different phases present inside the material. Okay, so if you don't get new peaks as compared to base metal, that means the new phase has not been formed. However, this XRD analysis shows the results at gross level. That means it shows the results at bulk metal level. So what happens at localized level, we have to do some more scanning. So we have to go through EBSD analysis as well as the TM analysis. So let's see what those analysis has brought up. Okay. So if you see over here, there were three kind of structures forming. Okay. Near the laser affected zone, very near to the laser affected zone, this is the structure. Okay, here you could see so many kind of dendritic structures. Okay, then after that the B structure shows some kind of dendrites or lats, but overall some kind of aqueous grain structures also. Okay, and after that there is at the C zone there is the aqueous grain structure with some boundaries where we could not see any orientation or anything. So like earlier we have seen this kind of boundary formation. Okay, so this boundary formation we could not index in ABSD scans. Okay, so that might be due to many reasons like new phase formation. Well, there is a heavy distortion of the material which is not been able to, where EBSD scans are not been able to index. Okay, so these are the few things could have happened over here. Well, yeah, and here we could see some of the beta phase formation. Okay, okay, let's go ahead. Yeah, so near the edge there are circulation. Yeah, these are the partial conclusions of this. Okay, and for every scanning speed we could see the same effect. Okay, yeah, for third scanning speed also there is the same effect. However, we could see that for third scanning speed the beta phase along the grain boundaries has been increased. Well, that has been increased because over here, uh, over here it could be because of we have given enough power, uh, enough laser power and laser scanning speed that was sufficient enough to convert this boundary into beta phase. Okay, so that's what happens when you do annealing and you go beyond beta transit temperature. So first of all, beta phase starts to form at grain boundaries. Then it will start to form everywhere else. Fine. So that's what has been started over here. But the laser power as well as scanning speed was not sufficient to go for this formation to go beyond. That's why it has restricted in this region itself. Okay, so to investigate more, see like why are this still, we could see some black lines over here, why we could not still index that with even EBSD. Okay, for that there could be one reason, or there is the twin formation. Okay, so that means at the boundaries over here, okay, those are the annual twin has been formed. So earlier in the first part of this presentation we have seen the twins formation due to machining. Okay, so those are called as the machine twins, or those are called as the mechanical twins. Okay, so here when the temperature is the driving force to formation of the twins, these are called as the annual twins. However, both has the compression nature. Okay, yeah, so let's go ahead with the TM analysis of those regions. So you could see in earlier slides, there are so many black points were there in EBSD scan, mostly at the region where the laser affected zone, where the laser has affected the material drastically. Okay, so we did the TM analysis of this. Okay, so these are nothing but the twins. Okay, so let's see. Okay, here also with TM analysis also we could have found able to found the twin formation. Okay, so the twins we could see in EBSD analysis, the same we have got reflected over here. Okay, so even in atomic level you could see the twins formation. Yeah, so then at the grain boundaries, okay, here also you could see many of the non-index points. Okay, yeah, so those has formed due to some of the other structure has been formed. Some of those form as BCC structure. and some of them has formed the orthorhombic structure. So will orthorhombic structure in titanium, that is nothing but the alpha double prime we call it, that forms when you do when you do annealing followed by quenching. Okay, that is mean you are suddenly cooling the material. That is the time where this orthorhombic structure could form, and this orthorhombic structure has not been indexed inside the EBSD scan. Okay, here also you could see this kind of structure over here. Okay, so this TM kind of structure shows there are heavy deformations inside the material. Okay, so this deformation has happened due to the laser treatment. So what happens in laser treatment is you are localized at the local point, uh, the heat is supplied. Okay, and other point, uh, when when the other points acts as a sink. Okay, so at the just a layer below the laser treatment, okay, that layer will try to expand and other layers will try to arrest that expansion. Okay, so that will cause some deformation inside the material, and those are nothing but the localized deformation, and that has been clearly visible in TM analysis. Fine. Okay, so how does it affects the machining? Okay, so here you could see when we subjected uh, the laser heated samples to machining and compared with the non-laser heat treated sample, I could see some variations over here. Okay, variations is nothing but here you could see this is the non-laser treated sample. Okay, so the force variation F max and F min, that variation is higher everywhere. Okay, in these three samples, whereas the variation has been lowered with laser scanning speed, sorry, with laser treated samples. Okay, yeah, so what we can see from that, okay, so we could see that the segmentation ratio, okay, that has been reduced. So the reduction in segmentation ratio, it indicates that the plastic deformation happening, okay, on the rake surface, okay, that has been reduced. So when the plastic deformation is reduced, that means the heat carried by that plastic deformation, that is considered as loss, so that loss has been reduced. Okay, so after that, once the loss has been reduced, okay, that's how the force variation also has been reduced. Okay, once the force variation will be reduced, you will get lesser uh, vibration on the cutting tool. Thereby you could improve the tool life and you could improve the machinability of that material. Okay, yeah, so this was the crux of it, right? So here you could see, and let's see why what exactly happening in the shear band, why it is means why this shear bands is not getting localized. Okay, so what happening over here is, yeah, here you could see in when you machine the non-laser treated samples, there is a localized shear band formation. Okay, whereas when the laser treated samples, since the grain size is quite smaller and even the hardness is quite higher in this region, there is a grain boundary strengthening effect we could see. Okay, so that means the localized plastic deformation has dispersed over the larger area, so that has reduced the force variation. So this is visible in every other case too. Okay. Yeah. So these are the conclusions from this. Like the flex dominant region is harder as compared to the combined flex region, followed by this grain boundaries on the bands. Okay. Then we have seen that the twins form was the compression twins. Okay, and higher hardness and flex structure resisted the formation of localized shear band. So the third uh, conclusion is the main conclusion of this study. Okay, so after that, what we did is, now let us say if you want to do machining or if you want to do a simple turning, if I want to know that what should be my depth of cut, if I do the laser treatment of that sample. Okay, or in a reverse way, you could say that this is my depth of cut. So what should be my power and scanning speed to do the laser treatment, so that the improving machinability would come in handy in use. So this is the predictive way we have achieved what should be the scanning speed and what should be the power, and given scanning speed and power, we could see how much depth of cut we could come up with, and that depth of cut should be subjected to machining. Okay, yeah. So here what we are doing is nothing but predicting the laser affected zone, or the depth at which the laser has been able to modify the microstructure. Okay, so here you could see this is the governing equation. That is nothing but we also call it as a heat equation. Okay, the heat source is given as the Gaussian heat source, the exponential with the exponential term. That means this Gaussian heat source, uh, it it takes the bell curve kind of shape. Okay, so that means at the where the laser beam is concentrated, that's where the whole heat has been concentrated and will spread across the material because through its conductivity. Okay, then we have established one more relationship of absorptivity with respect to the scanning speed. Okay, sorry, reflectivity with respect to the scanning speed. Yeah. Okay, let's go ahead with this, what we have seen. So we perform the laser treatment simulation. Okay, here you could see the heat flux, and because of that heat flux, how the temperature gradient has been formed. Okay, and here also we have kept the parameters similar to what we did to the experiment which we performed. So we have kept here also overlap as 70%. Okay, so what we saw after that is we took into account the thermal profiles. Okay, so what we have seen that the depth of penetration is already decided uh, by it's already decided by the beta transist region. Okay, so the beta transist temperature governs the surface modification. That means when the laser penetrates and the power is not sufficient enough to cross the beta transist temperature, your material will not see the drastic change in microstructure in case of titanium alloys. Okay, so when it goes beyond beta transist region or beta transist temperature, that's the region where whole microstructure will get affected. Okay, so here in titanium, the beta transist region is around 1300 kelvins or near to 1000 degrees Celsius. Okay, so with this simulation, we tried to see how much thermal gradients is formed beyond beta transist region. Okay, so based on that, we have decided the penetration depth. So here you could see the experimentation and numerical penetration depth. It is quite comparable with each other. Yeah. Next thing is the phase analysis. So with this simulation and with the cooling curves we could also see what could be the different phases formed in the material. Okay. So we have seen over here. Uh, yeah, we have plotted the temperature profile and seen with that temperature profile many of the phase could be predicted, like orthorhombic structure, uh, then BCC structure. Those formations were possible. So same has been established through TM analysis. So this is nothing but the validation of that phase predictions. Yeah. After that, what we try to achieve is, so let's see, here after giving laser treatment, we could see the penetration depth increases along the laser travel, like we see in the first part of laser treatment. Okay, yeah, over here. But as many of times we have to perform machining with constant depth of cut. Okay, in turning, especially in turning operations. So modifying the structure uh, at constant depth of cut, well, how that could be modeled? So for that we have defined a polynomial equation. Okay, how the power should be changed along the scanning speed, or the power could be changed along the time of laser scanning. Okay, so applying the boundary conditions over here, we have come up with this equation. Okay, so that P at x equals to 0 will be P minimum at it when it reaches at this level, it will be the maximum. Okay, and after applying these conditions and taking this dp at by dx at x equal to 1, here you could change, see the slope has almost become constant, means after this the laser penetration will become constant. Okay, so at that point we'll get the difference with of power with respect to uh, with respect to the scanning travel. Okay, that will be 0. So to get the constant depth of penetration, okay, we could plug in this polynomial equation and get almost a constant power. So here you could see, while plugging this that polynomial equation, we got the constant depth of penetration that has been revealed. If you could see this yeah, these sections, okay, for every cut, and that cut has been happen at 5 millimeter, 10 millimeter, 15, 20. Okay, at every interval of 5 mm we have got different cuts, and from that cuts, uh, from that cross section we could see how much is the laser depth penetration affected. Okay, so with this model actually already uh, we could get a proper or a constant depth of penetration. Okay, and with laser treatment we have already seen that how the machinability can be increased with reduction in cutting forces. So combinedly these two, okay, yeah, this model has been built up. Yeah, okay, so this is the conclusion of the last part. Like predicted phase change happened by time temperature plot. CCT curve has been validated through TM analysis. That means the whatever phase change we have seen or we have predicted, well, that has been validated through TM. Okay, twins has been formed. That is due to the rapid quenching mechanism and localized heating, and those twins are nothing but the same compression twins. Okay, then we have implemented this polynomial input power variation in FE model to result in the uniform distribution of heat penetration along the axis of cylinder. Okay, so what will happen when you get the uniform laser penetration, you can decide your depth of cut for machining. Okay, and with this model, you could get a constant depth of cut and go ahead with your machining and reduce the cutting tool cost. Okay, yeah. Okay, yeah, that's from my side. Any questions, guys?
Saitosh?
Yes, sir. Sir, there are some questions from the attendees. And first of all, thank you for the very insightful session, sir.
Thank you.
Sir, Tufan Kumar is asking, how does the grain size affects the machinability, sir?
Okay, so if you could see over here, grains, it will not affect machinability for every material. Okay, I was talking especially in terms of titanium. Yeah, so here you could see the cutting forces. Okay, the variation was quite higher when I was performing the machining at at sample which is annual at 925 degrees Celsius. Okay, and that sample has the highest grain size.
Okay, sir.
Okay, so what happened over here is since okay, I will put in one other way also. Like here, the depth of cut was almost near to the grain size of the sample. Okay, so when you have let us say depth of cut uh, is of the length of matching to this grain size. Okay, so when you cut this grain, then other grain will come into the picture, okay, of similar grain size. So there will be the local orientation differences occurring while machining. So that's how the grain size is affecting the machining. Whereas over here in this well, in this anneal condition, the depth of cut is far more than the average grain sizes. Okay, so that's why grain size has no effect while machining this lower grain size sample. but when your depth of cut is comparable with the grain size, yeah, it will have an effect.
Okay, sir.
Yeah.
Sir, so Ajay has a question that what are your views on deformation of high-speed titanium turbine blades, and do you have any comments on failure of Kaveri engine blades?
Oh, it seems hard to comment on that. Well, Kaveri engine turbine blades, actually turbine blades are not made up of titanium. Okay, it is made up of a single crystal, and it is made up of actually uh, high strength. What you can say, the inconel kind of material, which has very high strength and which is not chemically reactive at high temperature. Whereas titanium is highly chemically reactive. It's highly reactive at high temperature. You could not use that in a turbine blades. Okay, so what I would think is well, to the deformation when it comes to the single crystal. Okay, so your cutting tool motion and your cutting tool path, that governs the deformation mechanism. Okay, and every if your single crystal is oriented, it will be oriented in only in one, or sorry, your crystals in a single crystal will be oriented only in one particular direction. Okay, so there you need to find what could be the direction where you get lesser critical resolve shear stresses, so that your machining will have a lesser reactive forces, and it could be smooth, it could be more smooth. But yes, it compares to turbine blade, there are many other complexity associated. So, well, it will be hard to comment on my behalf for that.
Okay, sir. So Abhishek has one question that is there any way to do real-time monitoring on the material health when it is on a constant aerodynamic loading all time, sir?
Can you repeat the question again? Oh,
Sir, any type of monitoring for the material health when the
mhm.
material is under constant aerodynamic loading, sir?
Yes. You could do. See, uh, but it has to be done in the non-destructive way only. So one other thing you could do, you could see the with infrared cameras, like how is the variation happening, whether it is in constant loading or not. But for that also, there are many testing methodologies already been established. Like these materials are subjected to creep loading, relaxation loading, and very high fatigue behavior at high temperature loading. So after testing and all, it goes into it goes into the assembly. But yeah, well, the real time health monitoring you could do with many of the NDT testing which is available. uh, there are like ultrasonic waves which they transmit, okay, to see whether any crack has been initiated while the material is subjected to fatigue loading. And these are nothing but the preventive measures people carry forward with for health monitoring. And those all are considering with non-destructive testing. I would suggest you to see in detail what are the non-destructive testing which people carried forward for aerospace applications. Well, it and aerospace as well as the health. Sorry, the machineries. Okay, which will do the health checkups and all those things. So those also goes into the NDT testing. So if you could get details on that, that will answer your question.
Yes, sir. Ajay Kumar has another question that are there any softwares available for analyzing various parameters of materials during and after testing without actually testing them?
Hmm. So like while simulation is one way, okay.
Yes, sir.
Uh, while and what you can see is, see what we do when I had some projects in additive manufacturing. Okay, so what we found out that when we keep the material after making it layer by layer processing and subject it to the given loading, okay, that has created some problems. Intrinsic problems has came up later on. So what we did is we did the short peening of that laser treated sample. Okay, so that there are the compressive stresses was built up, and those stress hasn't allowed the crack propagation to grow further. Uh, well, another well, like you say, you have to go in deep with NDT testing to see, means every after 3 months or after 4 months how this material has behaved. Otherwise, what especially the automobile companies do is they take the engine out after 10 or 12 years, okay, and then they do many of the testing analysis of it. So how much wear and tear has occurred, uh, and how those wear and tear could be predicted easily without testing, and how this wear and tear can be prevented, or your life of the material can be prolonged. Okay, other way to see in a time basis is to keep the sensors. Okay, so like well, in our case, let us say we want to see in MRF tires, we have to see how the tire is behaving after it has crossed around 1 lakh revolutions. So what we do is we'll keep the sensors inside the tires. Okay, we could see how much is the now how much pressure the tire could sustain right now. Okay, so like there are different pressure sensors, then there are temperature sensors we put inside. We could see at what locations where my temperature has been rising up, and what my material could behave at that temperature, that I already know. So I will not allow my tire to pass beyond that temperature. Okay, so those are the uh, means online, you can say online data monitoring we could do. So same thing we could do on materials also, like if you have the infrared cameras, okay, and pointing towards the critical locations, you could see its fatigue creep behavior, okay, at constant loading or at variable loading. So with that temperature variation itself, you could build up your data analysis and next methodologies.
Yes, sir. Thank you. Sir, Nikhil had one last question, that which approach did you follow to calculate the forces that are produced during machining, sir?
So it is the it's a conventional way of measuring the cutting forces, that with the dynamometer, and it's a quartz type dynamometer. So what happens here is there is a quartz crystal inside the dynamometer. Okay, and when it's subjected to any forces, okay, so its resistance changes, and that transforms into a signal. So that signal converts the that signal gives in the voltage format. Then your there is NI software which converts the voltage into newtons. So volt to newton conversion is there. By that you can get the cutting forces. So you here, if you want to study in deep, you can go and see what are the types of dynamometer people use to predict the cutting forces in machining. It is the quartz type dynamometer.
Thank you, sir. I think all the questions have been answered. Now I would like to switch to Srinivasan, sir.
Thanks, Dr. Sagar Ji, for this. First of all, agreeing for this and delivering here and accepting the offer and the invitation and delivering to the participants. And I understand this three parts, the different parts of work you have presented, and all extensive, time-consuming experimental work. I know how painful it is EM and EBSD for titanium alloys. I really appreciate, and phase change is also very important. We need to understand, is this
Yes.
good thing or bad thing? This phase. For example, where my material, where I worked extensively, phase change. It's always, it's controversial topic now. Even though topic is open for more than 300 years.
Correct.
So this phase change, that's why we need to have the advanced characterization, tools, make use of this. And you have done EBSD and TEM. So why this topic we thought this is relevant here is, whenever we are on the mission of product development, whenever we are in the part of the team, the students and faculty members or the research scholars at large, we know nothing is superior, nothing is inferior, and this materials, behavior, we need to understand it completely. Then only, as a stakeholder, stakeholders as a team member, we need to, or at least to study next, not master, master of all. At least these kind of things, very important. The one of the main reason is product development management. Students, they should be able to have this the knowledge of both technical and materials and manufacturing, the simulation, and all these things. We need to have 4 or 5 different phases. I mean, multifaceted. So then only you will be a successful product development engineer. Okay, very thanks, Sagar. So in this line of thought, this session has been this, not only your session, from the day one to till now, we have been evolved, to achieve this mission. We have tried to focus on this. And very thanks, Dr. Sagarji. Thanks. Bye bye.
Thank you. Thank you. Thank you. I appreciate it. Thank you. Thank you all. Thank you for listening to me. Thank you.
Good afternoon, everyone. Now, I'm very pleased to welcome our next speaker, Dr. Dhruv Chandel from MathWorks India. Dr. Dhruv is an educational technical evangelist at MathWorks, based out of New Delhi. He works with universities across India to introduce computational thinking and model based design into teaching and research. He earned his master's and PhD degree in mechanical engineering from the University of Bath, UK. He has over 6 years of experience in multi domain modeling and simulation, control design system, artificial intelligence, and embedded programming. He has previously worked in academia as well as industry, including 4 years with startup renewable energy company on bringing a prototype wave energy converter to a commercial stage. His today's presentation is on the subject of model-based design for multidisciplinary engineering. Dr. Dhruv, you can start your presentation.
Okay, thank you so much. Just doing an audio check. Can you hear me clearly?
Yes, sir. Yes, sir, we can hear you.
Okay, thank you so much. I'll start sharing my screen.
Yes.
Just a moment. I hope my slides are visible.
Yes,
Yes,
sir.
sir. Yes, sir. Yes.
Okay, great. Thank you
Yes,
very
sir.
much. Yeah, good afternoon, everyone, and thanks for the kind introduction and the invitation to speak at this conference. So I'm very glad to be here with you today. I hope you're all having a nice time. I know it's Sunday afternoon after lunch, but I'll try to talk to you about something which is very interesting to me, and I hope it will be useful to many of you as well. So just to get a rough idea, am I talking mostly to students or faculty? I mean, who is in the audience?
Sir, both students are there. And
Audience, sir.
faculty are
Actually,
there.
it's a mixed faculty, research scholar, and the students.
Okay, excellent. So we'll try to keep the messaging sort of mid-level so everyone can follow. Okay. So the agenda for today, I think I have around 1 hour and 15 minutes. So I'll introduce myself. I'll tell you where I'm from, what my background is. We'll spend most of this seminar talking about model-based design. And then if I have time, I'll tell you a little bit about the modeling capabilities of MATLAB, Simulink, and SimScape as well. And I hope to have a lot of time for Q&A, but if you are confused at any point, so I'll pause a little bit between sections, and please feel free to interact. This is for your benefit. If you have any questions, please do ask, because interactive sessions are much more fun. But this is not a sort of product selling webinar. We'll be talking about a concept of model-based design and why it is useful in industry. Okay, so just a little bit about who I am, where I come from. So I work for the MathWorks, and we believe in the importance of engineers and scientists because they increase human knowledge and profoundly improve our standard of living. So we created MATLAB and Simulink to help them, that is to say you, do your best work. So MATLAB is one of the easiest computing environments that you can get access to these days. It's designed for engineers and scientists. And the other thing I'm going to be talking about today, most of the discussion will be on Simulink. So this is a block diagram environment for simulation and model-based design. And we'll see a lot more of this as we go on through the presentation. And these tools are not just useful for academia, but they're widely used across industries. So especially aerospace and automotive industries use these tools heavily. All the methods that we're going to talk about today are very heavily used in most of the safety critical applications that you will run across. I'm from an energy production background. I'll tell you what I used to do. But also if you're working in the area of communications or medical devices or metals, materials, mining, any of these areas, it's quite likely you'll run into these tools somewhere. And just to give you an idea, I won't talk about all of this, but the same methods that we're going to talk about today and the same tools are used by all of the top 10 auto manufacturers and all of the top 10 aerospace companies in the world. So this is something which is very relevant to industrial applications. And learning this might be a very good way for you to find your future work in research or in higher studies or in industry, wherever you choose to go, if you are an engineer or scientist. So a little bit about me, as they very kindly mentioned, I have a master's and PhD in mechanical engineering. I used to work in robotics research. So at the top right-hand side, you can see one of my robots trying to scan an industrial manufactured object. So this was a combination of mechanical, electronics, and image processing engineering. And we were able to take measurements of objects by scanning them from multiple sides. This was for an aerospace application where we would be trying to measure the dimensions of a turbine blade without having to physically go and touch it. Or the same for medical devices, because sometimes these materials can be quite sensitive to handling, so you don't want to damage them very much. So we try to optically scan these things. The bottom right-hand corner shows you another place where I used to work. This is a wave energy device. So this was a paddle. It was basically a U-shaped paddle put in the water. This was made of carbon fiber reinforced polymers, CFRPs. And the idea is that this thing would oscillate back and forth with the waves, and the motion could be used to run a small turbine. And from that turbine, we could generate electricity. So it was a renewable energy application. But as I hope you can see in both of these cases, this is not just pure mechanical or pure electrical or pure anything engineering. There are elements of all of these different things involved. And as the systems start becoming more and more complex, we have to start thinking about multiple aspects of these things, including the control systems, including the materials, what we're using, including the algorithms, because each part of them affect the entire system in a way. So that is what we're going to talk about today. And we'll see how to integrate all these systems. What is a good process for working on these kinds of multidisciplinary uh, domains. So I've been using MATLAB and Simulink for the past 10 years, but I've also worked with other tools. I've worked with, say, Fortran, R, C++, Python, then your ANSYS, COMSOL, etc. So I have a wide experience, but I now work with the MathWorks education team. And mostly I support researchers at universities and professors with curriculum development. So if any of you have questions afterwards, I'll be happy to talk about any of these areas, including modeling, simulation, control, robotics, AI, parallel computing, etc. Okay, so enough with the introductions. Let's get to the main topic for today. So what is this model-based design anyway that I put in the title? To understand this, let's first look at the conventional method of building a product. This is the way a student might think of how a product is built. And many people in industry still do a lot of this. So in the conventional design process, basically you start out with a problem statement or some set of requirements. Yeah. So the problem statement or requirements mean, what am I trying to design? What are my objectives? And what are my constraints? Right? So suppose that you are working in an automotive area. The last speaker, I really enjoyed his presentation, was talking about road tires. So maybe you're let's say an automotive engineer, and you have the objective that you want to build a car which can go 40 kilometers per liter and has a very nice mileage. Or maybe you're working on an electric car, anything like that. So you'll have to decide, what am I trying to build? How much should it cost? What should be the weight? Who is it being pitched to? Is it a race car? Is it something you drive on the road? Is it something that you will use only in the city, or it's an off-terrain vehicle? That you have to define these requirements right at the beginning, because otherwise you don't know what you're designing as an engineer. Now, after this, after we've set some requirements in place, we go and start doing the component level designs, or the subsystem level designs, as they're called. So the mechanical engineers will start thinking about the body, the chassis, the wheels, the powertrain, the engines. The electrical engineers will have a different set of tasks, how the power is flowing, what are the battery systems like. The control people will be working on how do we manage the control signals. So if you press down so much on the accelerator, how is the power going to be drawn from the engine? How is it going to be translated into the motion of the wheels? All these things they'll be worrying about. And then there'll be some embedded software people also working on the project. So modern cars are not just the body and the wheels and the engine. Modern cars have something like 100 million lines of code in them. So it's a very software engineering heavy job as well. The same is true of almost any environment you go to these days, whether it be aerospace, whether it be the materials industry, biomedical, anywhere. These 4 domains are very common across all of them. Now, finally, after we've built some of our subsystems, we try to integrate all of them. We try to put them together, and then we have a testing phase. Right? This is typically how engineers have approached problems, traditionally speaking. But as people started discovering in the 1980s and 1990s, this has certain problems associated with it, this approach. So what's the problem? Now, first of all, if we just come up with certain requirements and design specifications on pieces of paper or on backboards, it is very easy to misinterpret these things. And it's very difficult to analyze what these actually mean in terms of the system-wide implementation. It's difficult to manage these requirements as they change as well. Because suppose you started out to do one thing, your requirements changed over time, maybe the market shifts, maybe the technology changes through the design process, maybe anything happens, and you may have to go back and change what you were working on. It's a very common thing in industry. So it is difficult to go back to your original files and try to figure out what changes do I make now. Another part, your physical prototypes that you have to build. If you have to build a car or an airplane or whatever it is very expensive to build these kinds of things. You have to buy a lot of material. You have to have technicians involved in making these things. It costs a lot of money and it takes a lot of time. So you cannot iterate your designs rapidly. And there is no system level testing. There's no concept of system level testing because there, as you can see, there are barriers between the mechanical, the electrical, the control people. These are all people from different departments. Sometimes they talk to each other, sometimes they don't. The communication is certainly not perfect. So at the end, when you try putting all these systems together, the mechanical and the electrical parts may not be sized properly, or the controller may not be tuned nicely. Or you find out when you put the controller into your software, something messes up. There's some piece of code has a problem, which you did not anticipate. If any of you followed the launch of, if you're into aerospace at all, you might have heard of certain disasters which happened because the numeric bit type conversion was not implemented properly in the software. Certain rockets, I will not name the company, have exploded because they put sensors upside down and did not manage to test it properly. So this process, this traditional process has a lot of problems when it comes to designing for safety. It's also very expensive. Another problem can be manual coding. So after you've made your control system, after you know what your machine is supposed to do, you have to write the code. You have to sit down and hire programmers, and they'll end up writing the code. This is quite a time-consuming process, and it introduces a lot of defects, and they have to redo a lot of work because they have to replicate the knowledge of the mechanical, electrical control engineers inside their software. And finally, any issues in the design and the integration are found very, very late, right? So it is difficult for the testers to provide insight into what the designer are doing, because by the time they get something to test, the design process has already been finished or already run through a very large amount of time, and there's no traceability to the original requirements. So all of these are very common issues. They're more common than you would expect in industry. And no matter what domain of engineering you're from, these issues do turn up. Were there any questions so far? I was hearing some sound. Okay.
No,
If
sir.
there is any
Let's have it
question,
at the end of the session, sir.
I'm sorry.
Let's have it at the end of the session, sir. The questions.
Okay. Okay. Thanks. Okay. Let me just to tell you. I'll show you some data from NASA. This is a 2004 study on verification and validation. So on the, we'll plot a graph here. So on the x-axis, we have the project phase where the error is fixed. Yeah. And on the y-axis, we are going to plot out how much cost it is to fix an error. Okay. So suppose you're designing a spaceship, let's say a space shuttle. You have to first say what the mission of the shuttle is going to be, because that's what will define your design. Then you do your design, then you write your software and your coding, instrumentation, all these things, and then finally you test it. This is what NASA used to do. So now suppose that you're in the requirements phase. You're deciding what kind of mission your space shuttle is going to fly, right? I know this is not a core materials engineering thing, but there is a lot of material engineering also involved, because depending on how fast your space shuttle is coming into the atmosphere, that will change how much heat the surface feels, and that will change the choice of material, right? So I'm just trying to connect different domains. So just based on the trajectory of your mission, the material that you put in your space shuttle will actually change, right? So all of these have to be captured initially in what we call the requirements phase. And if you make an error in the requirements phase and you fix it immediately, there is a very tiny cost, because you've just started putting things together. If you spot an error, you fix it, no problem. Now, next comes the design phase. So if you made an error in the requirements phase and you catch it in the design phase, it is still not too expensive to fix it, because you can just go back one step. You can say our requirements had some problem. You make the change and you come back to the design phase. Of course, if you catch an error being made in the same phase, it's very cheap to fix it. Probably a few weeks of engineering time. The problem starts becoming worse as we go down the project. Okay. Next comes the coding phase. So suppose you planned your mission, you did the design. Now, when you start programming, you realize that there was some problem right at the initial phase, the requirements phase. So now you have to go back 2 steps. And in the requirements phase, you have to change everything again. You have to come up with a new design and you fix it here. So this is more costly again. Of course, you'll have to change your design. There's more cost. Again, if you catch the coding errors in the coding phase, not much problem. This is okay. The real issue is, if you do all of these steps and then during the testing phase you catch your error, just look at the cost. I mean, that is huge. I've not put numbers there intentionally because numbers change due to inflation and all that, but just look at the ratios. So requirements is what your mission is supposed to be. If you do your design, if you do your coding, programming, instrumentation, all these things, and you catch some problem in the testing phase, there is a huge cost associated with it, because everything you did over the last few years is completely useless. You have to go all the way back and you have to repeat all these steps. So this is what we want to avoid, this big red spike here. This is what we want to avoid. And same thing, your errors in the design phase also escalate in cost. Your errors in coding are okay. I mean, you can catch it here, it's fine, but they're also best avoided. So model-based design is a workflow or process which was invented by the German automotive industry in the 1980s, along with MathWorks. So MathWorks was a big pioneer in that. This was adopted by the aerospace industry, and now many other industries, the medical devices industry, and all those other pictures I showed you, they are all starting to use these processes. Now, model-based design can help in preventing this. This is that big red spike where you make a mistake at the beginning and you catch it at the end, and it ruins all your work. Okay. The way this works is, we first have requirements and specifications. So this does not change. But immediately, as soon as we have our requirements, we spend a little bit of time building a multi-domain simulation model. This will include some control systems, some electrical, mechanical components, and a little bit of software as well. This does not have to be a detailed model. It can be just a rough model, a rough outline, maybe even just a few equations. And immediately, as soon as you make the model, by model we mean mathematical model, we compare it against the requirements. And immediately we check if our requirements are sensible, and this can help us produce better designs. So suppose your boss or your client comes up to you one day and says, I need a diesel car which can go 40 kilometers per liter. So you can't just say no to him. Okay, that's not good engineering. That's also lazy in one way. But what you can do is you can ask him, how many people is the car going to carry? What kind of road is it going to drive on? Yeah. If it's just driving on a highway with one person, which is almost like a motorcycle, you might be able to get that mileage. So you have to capture these requirements in the beginning, and you check if the mechanical and the electrical and all these systems make sense. You may only have a few of these systems, you may not have all of them, or you might have more things. You might add materials here, you might add chemical systems here. But the point is you capture this information right at the beginning, and right from the start, you start cross-checking between these things. Is the design making sense, and are our requirements sensible? Now, what you can do is once you start developing this process, you can go into the details. You can start designing your electrical circuit. You can start choosing your mechanical materials. You can start building your control systems. And then you can test everything inside simulation. So if you test everything in simulation, that reduces your chances of making an error in the design phase. And that means your hardware prototypes have a very much lower cost. So if you remember the robot thing that I showed you, or the wave energy thing that I showed you in the beginning, the cost for one of those devices was approximately $250,000. So I was working in a startup company at that time. We could afford only one device, not more than that, because we didn't have money. So what we did is we made around 500 different kinds of device models, everything inside simulation. We tested them all out. We picked the best 20 designs from just a rough simulation. And then those 20 designs, we did a detailed simulation of how the wave interacts with the structure. Is my carbon fiber structure strong enough? Are my motors turning fast enough to generate current? All these things. And from that, we were able to select one or two good designs, which we eventually manufactured. So the cost of your hardware prototypes fall. And because you're simulating things, you can catch errors very early on. So if you had any mistakes in your requirement or your design, you can catch them very early on in the process. And of course, everything is integrated. So your electrical circuit will be of the right size for your mechanical system. Your materials will be of the right configuration. Your control strategy will take all this into account because you have been simulating all of this in a single mathematical model. Okay. So this is the model-based design process. And what we'll do in the next 45 minutes or so is we'll look at the steps of how these things are actually done. We'll look at it step by step. Right. So the workflow looks something like this. This is called a V-shaped process. And I'll tell you what this is. So the first arm of the V is called the design phase. And in the design phase, we start from the top level system and then we start going into more and more detail as we go along the design. Okay. So first we define the requirements of our system. Then we make a system level specification or a system level model. Then we do the subsystem design. So after we have the entire system, then we'll go and look at the individual components, the electronics, the mechanical, the blah, blah, all these things. And then finally, after doing these three top level processes, we go to the implementation stage, which is where you actually start investing money into this. Before this, you are just doing programming. After this, the second arm of the V comes in, which is the testing and integration phase. Some people call this the validation verification phase. Now, after you have made your designs for all of your subsystems, the mechanical, the electrical, the control, all of these, you check them at the bottom itself against the subsystem designs. So if you designed a mechanical component, you designed an electrical component, you have the control system, you put all of them together in simulation, and you check if they all are working with each other, if they are all the right size and shape, and they basically match. Next, you do the system level connections. So now you put together different subsystems into the whole system and you check if everything is working properly. And finally, you can complete your integration and then deploy your device. So basically, you start from the high level, you go down into the details, and as you're coming up the other side of the V, you keep on checking every piece of your work. So this process is called a continuous verification validation process, and this is what is being used by all of the safety critical industries today. I think at least most of them. Of course, at the end, if you've done all these steps, you can realize this is much more complex than just building a CAD model, because the CAD model is just this piece, right? Many of you are mechanical engineers, you know what working with CAD models. So this is the CAD model here. This is the physical prototyping here. But what you've done is you've added many more steps. So there's a little bit more work. But after this, you can be sure that your design is going to work, or you can be more confident that your design is going to work. So let's look at some industry examples of where this is used. After that, I will show you just like a rough outline of how we can do this for a car. So this is an autonomous aircraft. It's called Aurora. The company is called Aurora. This is the Centaur aircraft. It's an autonomous aircraft. And this basically can fly itself without a pilot. So let me pause here for 1 second. Now, if you think about this aircraft, there are so many interacting systems here, right? You have all of the mechanical parts of this plane. So you have the propeller, you have the engine, you have the flaps and the ailerons and all the control surfaces here, the elevators, etc., etc. Think about the materials engineering and the mechanical design of each of these gears. It depends on the total weight. This aircraft will also have some batteries, some navigation, some radar in the nose, some communications equipment. All of that has to work together. There is a control system inside the cockpit, so you'll see it moving in a second. So if you look inside the cockpit view, there will be like a joystick moving and controlling all of these systems. Back up here. So all of this instrumentation has to take readings from the engine, and then the movement of these joysticks will change how the aircraft is behaving. All of this has to be connected together, so that's the electronics part. And because this is flying autonomously, there is obviously going to be some software there for the artificial intelligence. So all of this, they simulated this entire aircraft first using model-based design, and they were able to get basically their first prototype working. So imagine you had to build 100 of these aircraft. It would be very expensive. You know, if something crashes, it's very dangerous because airports are typically in populated areas. But because they followed the whole process, they were able to get this working the first time, flying safely, and you can see the actual prototype there. Another design, this is from an Indian startup called Aether Energy. I believe they were incubated in IIT Madras, if I'm not mistaken. So what they were trying to do is design India's first intelligent electric scooter. And if you see the quote, they say, we had lots of promising ideas, but as a small startup, we did not have the time, money, or people to build prototypes to test each one. So with model-based design, we identified and validated the best ideas through simulation, making it possible to deliver a full-featured scooter in less time. Now, they basically were able to reduce their testing time by 50%. What I want you to think about is the complexity of this scooter, right? You have the mechanical design, obviously. You have the placement of the wheels. That will affect how much forces are going through the spring. If the wheels are designed properly, the forces going through this suspension might be smaller, so you can get away with using cheaper materials. This is an electric scooter, so obviously it will have a battery pack inside this place. It will have some charging system, some microcontrollers to control the charging circuit. If you can model how fast the scooter is going to be ridden through what conditions, you can choose the materials in all of these surfaces such that they can dissipate the heat from the batteries properly, so there is no danger of catching fire. And of course, you will have a control system. So based on how much you turn this, this handlebar, some amount of power is going to be delivered to the motors or the brakes, whatever it is. And based on that, the control system will help you manage this scooter properly. So even a very simple thing, this costs, I think, 40, 50,000 rupees, something like that. It might be more if I'm not wrong. There is still a lot of complex engineering that has to go into these kinds of things. So if you can model all of the different parts of this, you can see how each bit affects every other thing. And that just increases your chances of success. I'll leave this in the slides, but basically the same thing has been used for the Airbus A380's fuel design. So if one of the engines goes out or one of the pumps fail, the aircraft can still keep on flying. I'll just skip this for now because we've talked through examples already. Okay, so why are these industry use cases successful? Basically, there is some benefit to continuous testing and validation. That's the core idea that we're trying to get across here. So the requirements are linked to the model. You have some requirements where you start out with. And based on these requirements, you create some models. So these include models of the environment. What is the temperature, the pressure, the vibration, all these things. You can design your physical components. So let's say you have made some mechanical design in a CAD software. You can import it here. Let's say you have done some analysis in a software like OpenFOAM or ANSYS or whatever you're using. You can take those inputs and you can put them into your simulation model for designing. You can also check if your algorithms are properly done. And at every stage, as you're going through this process, top to bottom, you're continuously doing test and verification. You're comparing if your design meets the requirements. So you also check if your controller is working properly. And then in the implementation phase, what model-based design proposes or supports or recommends is that the code which is coming out of this, so C++ code for your microcontrollers or VHDL Verilog codes for your FPGAs or ASICs, or code for your PLCs, etc., etc. This should not be handwritten, but it should be automatically generated from your model. So basically, what happens when people are writing manual code, there is a chance of having errors, and there is a lot of replication of work. So in the ideal model-based design workflow, based on this design that you do here, the code should be automatically generated. I can talk a little bit more about this in the end. And then you do your integration and testing. But by the time you get here, you've already done 3 rounds of testing, at least. So the chances of your system failing down here are much lower. And therefore, you don't get that big red spike, if you remember, of cost. Because you keep on catching errors and fixing them at every step. And at the end, your system should work, hopefully in the first try or the first few tries. Okay. Any questions so far? Would you like to save them for the end? I'll check the chat quickly.
Questions are there, though, sir, in the chat. If you want, you can answer it, or finally, if you want to answer it, you can also do it. It's up to you.
Okay, I'm just trying to read the chat.
Savidush, can you help out those, sir?
Yes,
yeah,
sir.
I got it open. Thanks.
Okay.
So first is how to do simulation analysis of microstructure of stainless steel. If you know the equations, you can write code in MATLAB to do that. Otherwise, this is not the ideal software. I mean, I would recommend you use some finite element analysis software. Otherwise, the PD toolbox is there, partial differential equation toolbox. So with that, you can do some amount of modeling. Simulation analysis of unique microstructure of strain-induced Martin set. I think it is the same question.
Yes, sir, it's the same question.
Yeah, it's basically the same question. Yeah, try the PD toolbox if it fits your thing. I'll just write here. That's the partial differential equation toolbox. But what we're talking about is more systems level engineering here. What you're talking about is component level modeling. So for component level modeling, I would advise you pick whatever tool is best for that domain. It might not be MATLAB, it might be some other tool also. Okay. I can't see any other questions. If there are, please ask. Someone has asked microfluidics use of MATLAB. Please reach out to me afterwards because I would need to understand the problem. So then I'd be able to advise you. I've definitely used Simscape fluids for doing a lot of fluids work. So just reach out to me afterwards. You discussed the V model. Are there any other such models? I'm sure the management people in engineering would know a lot more about them. As far as I'm aware, for systems engineering, this is the main model which is proposed. And of course, I'm talking about this because I've used this before. I'm sure there must be other models, but this is the one that most of the industry is using. I can tell you, if you take any of your big aerospace companies or even NASA, they're using the same approach for most of their systems. Most of the automotive companies, I mean, they invented this, so of course they're using this. And many other industries are also transitioning to this. So I hope that helps. You can check in some management books. They might have more models. I'm not aware of any that are this successful. Okay, so now that we have some idea of model-based design, where to get started? So you can start off with, first of all, learning how MATLAB Simulink and Stateflow work. So these are tools which are built to help you design complex and robust software without having to handwrite a lot of code. So MATLAB is a language for technical computation. Simulink is a platform for model-based design. So Simulink models look a bit like this. You basically have different blocks, which are mathematical functions. You supply some input, they will give you the output. And all of these blocks are calculated in parallel. So you can run a simulation. I think this is a PID controller for a helicopter type system. So the helicopter is returning its current position. The response is going back. It is being compared against some demand position. And the controller is going to try and follow and keep this helicopter flying properly. So you can use Simulink basically to start out with. I'll share the resources where it can be learned. And then a third tool is called Stateflow, which is used for modeling state transition diagrams. So if you're working with control systems logic, where you have different kinds of operations, different kinds of states, Stateflow is a tool which is very popular for this. It is used to model how the control logic flows. And all of this can be automatically generated to C++ code. So if you can build a model like this, what this is doing is, I believe this is for the Mars landing rover. So if the altitude is above 10,000 meters and there is no anomaly, it just stays in the entry mode 1. As soon as the altitude drops, it goes to another mode where the parachute is deployed. And there is some option for aborting as well. So I'm not exactly sure where this is from, but this is the kind of code which is often used for systems where they have different modes of operation and where the system has to automatically decide, do I do this operation or not? So if you go to this link, matlabacademy.mathworks.com, I'll share this in the end. There are a bunch of courses there. So there is MATLAB, Simulink, Stateflow, on-ramp, and now we've added machine learning, deep learning, image processing, and control design. So if you want to learn any of these, you can go to this link. And I think these are 2 to 3 hour long courses. They all run from your browser, and you can get a certificate for this at the end. And these are all free courses. You don't even need a license for this. Okay. Basically, the most important thing for model-based design, I would say, is Simulink. So Simulink is a platform that looks like a blank canvas. You basically drag and drop blocks to create circuits. So this is an electrical circuit. You can also make a mechanical circuit, a fluid circuit, a thermal circuit, or you can have all of them in a single model also. And this allows you to model and simulate your system because you can have multi-domain models interacting with each other. So suppose you have this resistor. If you model the heat going outside it and connect it to a thermal circuit, you can model how the heat is being dissipated in some electronic circuit. If you take let's say the output across this MOSFET or whatever it is, that can be used to drive a mechanical system such as a motor. So everything works in a single environment. And this allows you to simulate and test a lot of different things. If I have time at the end, maybe I can show you a demo or something. It's not part of the plan for now. And the idea is that you can change these blocks very rapidly. You can change the parameters. So you can just double click on one of these blocks. You can change the value inside. And you can go and test hundreds or thousands of different conditions without having to invest in any real hardware. So instead of having to buy 100 electronic boards to test which one works, or even relying on equations, you can actually simulate this with the PID controller. This controller is basically software. And you can check if everything is behaving properly. And then, of course, at the end, once you've developed your controller, you can generate the production quality C and HDL code directly from this. So there's no hand coding required. Once you develop the model, this model is software. It's also your multi-domain system, and the software is automatically created for you. So this would be the good place to get started. Let me show you how this actually works. Let's say if you want to design a car or something like that, what the process looks like. Okay, so suppose that we want to develop a hybrid electric car. We will use the V-shape model, and we'll talk about how all of the steps for that car can be done. So the first thing is we'll define requirements. We'll look at system level specification, subsystem design, then implementation, and then we'll look at what is done in the testing phase. Now, this is a very complex system because you've got sensors, you've got mechanical, electrical, you've got your wheels, you've got your driver profile, engines, controls, blah, blah, blah. There is a lot of complexity here. But following this process, it is possible to manage this complexity and basically be successful when working with this kind of system. Okay, so the steps are, there are 7 steps. First step, you have to define your requirements. And you have to do this as early in the development process as possible to find the errors in time. So let's say you have a hybrid electrical vehicle model. The first thing you will do is specify your requirements. What is it that I actually want to do? And you will make the model based on those requirements. So maybe I want to convert this existing car into a hybrid electric car. And after that, we will define what each part of the subsystems do. So now at the system level specification, maybe what we want to do is develop a control system which will get my wheel to within 5% of the specified speed in less than half a second. So this means, for example, if you enable cruise control on a highway, we don't do that much in India, but outside this is very common. So you can specify, let's say 60 kilometers per hour on your cruise control. So your car will go up to that speed and it will keep on driving at that speed until it detects some obstacle or some change in some way. So this is very commonly used while driving on highways there. As autonomous cars start coming into the Indian market, we'll start seeing more of this. So you guys should be training for the future, basically. And these are the kinds of problems you will run across. Now, if the wheel has to get within this speed, we will have to look at the speed at which this car is currently driving. We would have to have a model of the braking system, of the batteries to estimate the state of charge, and a model of the engine. We may want to understand what is the interaction between the road and the rubber surface of my tire. So that might be in the form of a lookup table or a 2D graph, which you can pull data from, because the properties of your material will change, and that will affect how your car is driving at different speeds, at different temperatures, etc. And basically, because you have specified that this is what I want to get to, now you can go to the subsystem level and start designing out each part of this. You can also think about things like gear ratios, etc. So depending on what gear ratio you want, that will affect how much strength your material should be. So you will have to decide what kind of steel is going to go in there, or if it's some kind of carbon fiber, or I don't know what they're using for the powertrain these days, but your material selection will also depend on the control and the mechanical requirements. Okay, so that is why I want you to understand why system level specification is so important. You cannot do your job if you don't understand what the system is trying to do. And this feeds back into your design, and the design feeds back into the requirement to make sure everything is sensible. Okay, next step. Now we get into the subsystem design. So this is the place where most of you have been talking and where most of your studies are focused, I imagine. So you'll start looking at components, you'll start studying the details of each of these components. And what you might also do is you might go to other tools to do your detailed design. So you might go into some CAD software to make some 3D design. You might be doing finite element analysis. You might be doing CFD analysis. CFD is computational fluid dynamics. So these are specialized tools that are available in the market. You might be using a few of these. Now, when you get your outputs from these detailed tools, you don't just put them in a report and forget about them. They go back into your design, into the system level model. Okay, so your requirements came from the system level model. You go into some third-party tool, or if you have your own code in MATLAB or Simscape, you can do the detailed design in the single domain tools. And then you verify that by putting these outputs back into your system level model. Because otherwise they're not so useful. You have to test if it actually works. It's not just coming up with a design, it's also testing, remember. After we do this, then comes the software part. So then typically it hands over more to the software side of things. From your model, you generate the C code for your controller, and your Simulink model becomes a plant model. Plant is what we use in control systems. And we do things like processor in the loop testing. So whatever code you have generated, you actually put it on a piece of real hardware, and you see what effect it has had on your memory limitations, on your code optimization. Are your variables being converted properly? Are they of the right type? Are there any problems with sign changes, units, etc.? So all these things are tested. This is called PIL testing. And then after that, you can also do HIL testing, hardware in the loop testing. So basically, you take your controller and you put it in a real vehicle or some subsystem of the vehicle, and then you run your real controller with that real hardware, and that will allow you to check your system's doing what it should be doing. Maybe you've seen certain examples of this. I'm sure as materials engineers, you will have seen those testing machines in your labs which do the stress strain analysis and all these type of things. So what you might do, if you're an advanced user, you will have a profile of what kind of loads are being experienced on your real system. You will take those loads and feed them as force inputs into one of those testing machines, and you will see the outputs of how your material is responding. And that is one example of hardware in the loop testing. You can also have your engine in the loop. You can have your tires. You can have your battery management system. You basically test out each part of this. And then at the end, you put these together and do the complete system level testing. This is called the integration testing. Now remember, you have checked at this point each single component you made, each system you made. So you've checked the electrical system, the mechanical system, etc. Now you check all of them are working together as well. They've all been designed together, certainly. And if it works at the end, which it should, we can now be confident that our design is good because we have tested it properly. And one more thing I forgot to mention, this C code that you generate, your code also has to be tested, by the way. You cannot just put out uncertified code these days. So code has to be generated to certain standards for automotive or aerospace or medical device or electrical industries. So this automatic code generation prevents you from having to write all that code. All the tests are automatically generated as well. So by the end of this process, every part of your system has been tested individually and with each other, and you can be sure that it's going to work or reasonably confident. Okay. I can't see any other questions so far. So in summary, what we do in model-based design is we make a system-level simulation model which mathematically can describe complex behavior. This treats the model as a single source of truth for capturing requirements. So there's nothing on paper, there's nothing in files, it's all in the model. If it's not in the model, you can't be blamed for it, basically. Okay, all the teams have to work together on the same thing. It provides a solution for how you work with multi-domain subsystem modeling. And because you're continuously testing and verifying it, your whole process is more likely to be successful. And finally, you automatically generate the code from whatever designs you've come up with. So model-based design covers all of these areas. And I know most of you might be students, or most of you might be working in just one area where you're doing just the modeling process for one thing. but it is good to have a perspective on how the systems are put together, because the entire world is now moving towards systems engineering concepts. So if you want to train for the future, just keep these things in mind and basically start thinking about how you can develop system level simulations models. It will, I mean, I'll tell you more about what industry is looking for in students, etc. just after this bit. I believe I have around 25 minutes left. Are there any questions so far? We have time for questions. Is there anybody confused about why we are doing all these things?
Sir, we'll have a questionnaire at the end also. So before that, I just wanted to ask one question.
Yeah.
Sir, does the model-based design leaves other product development tools like FMEA redundant, or should we still practice them to ensure a safe design?
Good question. Yeah. So as I showed in this step back here, you should definitely be learning all the important tools of your domain. Okay. So model-based design is a method to engineer the whole system, but you still have to learn the single domain tools for modeling each part of your system. Okay. So if you're a materials engineer, let's say, you have to understand how the rubber in this tire is going to deform at high speeds, which means you have to learn the tool of that area. I used to work in wave energy. That's what my PhD is in. So I used to model the waves in the water using a particular tool other than MATLAB Simulink. I used to get the outputs and then put them into my simulation, because then I would be able to model if a wave of this much height comes into my system, this is how much force will act on it. And then after that, my simulation told me, okay, these are the forces on your mechanical design. I would take those forces, I would put them into something like ANSYS, which would tell me if the structure can take that much force. So you are still working with 2, 3, 4 different kinds of tools, and those tools are feeding data to each other. The point is that the system level model will be able to see everything. So this is like a monitor which can see everything, and you still co-simulate with all the other tools. Does that answer your question?
Yes, sir. Yes, sir. Yes, sir. Thank you, sir.
Okay, great. Okay, so I'll tell you a little bit more about how you can do modeling in particular, because many of you might not be aware. Let me skip forward through this. So modeling and simulation lie at the heart of model-based design. Let's quickly look at a few things you can do with MATLAB and Simulink in particular. I'm not discussing other tools here because my knowledge is limited there. So there are fundamentally two different approaches for modeling dynamic systems. One is called the first principles modeling, and the other is called data-driven modeling. And this is not a binary on-off switch. This is more like a spectrum. Okay. So if you do pure programming, if you are modeling differential equations and block diagrams, if you're using Simscape language or symbolic mathematics, that is all called first principles modeling, because you have some equation, and based on your first principles of physics or mathematics, you are modeling that equation and you're seeing what outputs you're getting. So if you're using other third-party tools, that will also go here. That will be another separate category down here, because those tools will be using partial differential equations or some understanding of material science to come up with some answers. On the other side, we have purely data-driven modeling. So if you have some laboratory data, if you have some test rigs, you can take measurements and then you can fit those measurements to some curves, and those curves give you a rough idea of how your system is behaving. So if you do the stress strain analysis by breaking those metal rods, you have those testing machines, I guess, in mechanical engineering, or you're working with, let's say you have some beam, you put a little bit of force on that beam, you see how much it deflects, then you put more force, you see how much it deflects, you do that test 100 times. That will give you a curve between the stress and strain, or the curve between input force and deflection. So these are all data-driven methods where you're actually measuring data. So there are a wide variety of capabilities for all of these things. So if you want to use statistics and machine learning, there's a toolbox for that. There's a toolbox for system identification in MATLAB. There's a toolbox for deep learning. So all of these things you can do with the data-driven one. And the first principles, of course, you can use your other softwares, or you can do first principles programming. What I want to talk to you today is this very interesting thing which is called physical networks. Okay, and these are a combination of first principles and data-driven modeling. They're somewhere in the middle. So the reason we use these kinds of methods is that if you look at this graph, you have less detail on one side and more detail on the x-axis, and you have slower simulation and faster simulation on the y-axis. So if you use first principle models, just equations, they're very fast, but they don't have much detail because you typically have linear systems. If you go to your CAD or FEA or partial differential equations, you will have a lot of detail, but the simulations take a lot of time. Because even if you're considering a simple bracket like this, you have to make a mesh, you have to check how much everything is deforming, and just modeling one piece will take a lot of time, but it will give you a lot of detail. So in the middle, we have something which are called physical network models, and the tool we have for this is called Simscape. So this is what I'll talk about right now for around 5 minutes or so. And this gives you a moderate amount of detail at a fairly rapid simulation speed. So the way this works is there's a library called Simscape inside Simulink, which can model all these different kinds of systems: so electrical, hydraulic, mechanical, thermal, liquid, gas, etc., etc. And you basically, let's say you have this kind of system, which is a rotating spring damper type system. You can just make a physical network out of this. If you had to draw this on paper, this would be the network you would make. So there are springs, dampers, inertias for all these shafts, etc., etc. And this will give you a very quick and fairly accurate idea of how much force and how much torque is in this system at each point. So this has more detail than an equation-based system because you can have these shafts as slightly flexible, which you cannot have with linear equations. It's very tricky. And you don't need to do the full finite element analysis either, because that will take too much time for any realistic system. So the advantage here is you just assemble a schematic like this. It's literally just a block diagram. You don't have to write any code. All the equations are derived automatically, and this runs from inside Simulink. And you can do this for all these different kinds of networks here: electrical, hydraulic, mechanical, thermal, blah, blah, blah. And there are advanced libraries for doing more detailed things. So there's a library for power systems for modeling three-phase networks, electrical networks. If you want to model electronics, which is MOSFETs or other kinds of semiconductors, power electronic circuits, you can use Simscape Electronics. If you want to work with fluids or hydraulics or vapor or two-phase fluids, you can use the fluids library. Multi-body I'll talk to you more about. This is for modeling joints, frames, bodies, etc. And driveline is there for automotive applications. So it has gears, lead screw, clutches, tires, engines, etc. So you don't, suppose you want to make a system level model of a car, you don't have to understand each part of this. You basically make a rough model of a car using the driveline library. And then whichever part you're interested in, you go into that part, and then you can use your specific, detailed domain specific tool to work on that and still be confident that you're coming up with a realistic design. So this will give you something like 80-90% accuracy, and with your tool you can go up to 95-98% accuracy. So it's very robust. It's a very good approach for modeling complex systems. The multi-body one is very interesting for mechanical engineers. All of you, or most of you, are from mechanical backgrounds, so that's why I'm mentioning this. What you can do is, I'll just show you. So if you have a CAD software like this, let's say I'm using SolidWorks here, and you have to build this assembly. So this is a hydraulic lift platform. You have these linkages, and you have a hydraulic piston driving these linkages. Now, why is a systems engineering approach important here? All of you are materials engineers. You can run some ANSYS program for this beam, right? You can check how much this beam is deflecting and all that kind of thing. But actually you can't get the right value of how much forces are being applied on these end stops unless you know how much load is sitting on the top, unless you know how much friction there is in this motion, and at what speed the hydraulic actuator is moving, right? Because how fast this accelerates is going to change how much force there is on this joint. All of your mechanical engineers, I hope you will appreciate this. If you just put 10 kilos on top of this, it will apply 10 kilos of force, or 5 kilos because there are two of them. But if you take the system and you start pushing upwards at a high velocity, then that, the pseudo acceleration force, the inertia, will add some extra forces on this joint. So doing the system level analysis will let you understand what extra forces there are on this beam, and then you can go and refine the design using whatever software you like. So what you do in SolidWorks is you just go and export this as an XML file, and then you can go into MATLAB and use this command called smimport, and that will automatically import the entire geometry. And from that, you'll be able to get the system level model. You don't have to make it yourself. You'll see the whole model is assembled for you. So you just type smimport and put in that command. So you can see all of these are solid parts or STL files. If you want to import this XML file, you just type smimport hydraulic lift 1. And we can specify the model name should be the same, hydraulic lift 1. You hit this in MATLAB, and in one line of code, you basically get an assembled system level model, which looks like that. It's all connected together. All the joints, all the constraints, everything will be modeled. And if you run this, you'll be able to see a 3D animation as well. So now you can put in whatever force you like in your piston, for example, and then do the further analysis. So as you are from mechanical materials background, I thought this might be interesting to many people. Right. So that's for physical networks. The other side, if you want to work with data-driven modeling, there is end-to-end support for machine learning and deep learning. So you can access data from your files, sensors, databases, etc. You can work with big data. You can clean it up. You can clean up the noise. You can extract the features. You can develop models. So if you're working in machine learning or deep learning, there's a lot of support now. I think it's one of the easiest platforms to work with. And then you can, again, put this as part of your code in Simulink, or you can develop apps, or you can push this code to embedded devices. So this end-to-end workflow is there. If you want to start off with this, just ask me the question. I'll tell you where the on-ramps are. And all of the things that we've talked about today support production code generation. So if you can do the modeling and simulation part, forget about all the rest of this. MATLAB will do this for you. So your C, C++ code generation, HDL, PLC, GPU, and it works just fine. Okay, so therefore we can use both first principles and data-driven models for our system. So in summary, these are all the things which you can do with MATLAB and Simulink. Multi-domain modeling, which we've been talking about mostly, but also the parameter estimation, control design, automatic code generation, working with big data, optimizing your designs, AI, and then integrating it with your enterprise systems. So these are the three things which we briefly talked about today. I think, okay, finally, what is industry looking for new students these days? So as you all know, there's a lot of economic turmoil now, and the job market is very difficult. I'm not going to lie to you. So if you're interested in getting a job, industry is looking for more depth and breadth, more conceptual understanding, and knowledge of industry relevant computational tools is essential nowadays. Okay, just knowing the theory is not enough. You have to know how to apply these skills as well. So a little bit about control, a little bit about verification, validation, software stuff, which we've been talking about today, and experience with complete projects and products, not just silos of theory. So these things will greatly improve your odds of getting a good job and then having a great career afterwards. because silos of theory, I mean, we can get specialized software now to do almost everything. It's the complete top level view, which is adding a lot of value. And finally, the ability to work with teams. So your soft skills, how you talk, how you interact, how you work with each other. So if you can find a few projects, work with a few teammates from different domains, you will end up acquiring a lot of these skills, and there will be a lot of value to you in in your studies. So more for the teachers here, how do we get our students to this level? What we suggest is, just like we have mathematics in our curriculum, in the first 2 years, you have your calculus and your linear algebra, etc. This is for an electronics course, but the same concept applies. As you are learning the core mathematics courses, the students are also using these in other courses. The mathematical skills are part of other courses as well. But in computation, what we find is that students do programming in first year, and then they do a project in the final year, and in between they've forgotten everything. So what our suggestion is from MathWorks side is that if you can introduce coding or programming or model-based design as part of other courses, such that the students keep on increasing their computational skill as just as they do with their mathematical skill, this really improves their ability at the end, and they can also learn much better using these things. So I personally was taught in this way, and it was definitely beneficial to me. If you're interested in, I think VIT already has a campus-wide license, so no need for me to sell anything. But if you're from other institutes, we now have this offering called the campus-wide license. So all students, all faculty get access to all the tools, and the price is also not that high. So if you're interested in this, you can reach out to me. And what my team does is we support the research and the curriculum development, etc. So this is the link that I'll just share with you. I'm at the end anyway. You can go online and you can do the free courses, and you can then get started off with MATLAB and Simulink if you're interested. So I hope this presentation has made some sense to you. If there are any questions, I can take them now.
Yes, sir. Thank you for the very insightful presentation. So there are some questions from the attendees. So Sanjay is asking, are the equation for components like suspension, damper inbuilt in these blocks? If so, how the inputs can be given?
Yeah, everything is inbuilt. Let me open MATLAB. This will take a couple of minutes to load because it's in one of the deeper toolboxes. So I'll show this. Are there any other questions while this is opening?
Yes, sir. There's a question from Nikhil that what programming language is good to learn for mechanical engineers in case of simulation or system development while using this software, sir?
Right. So I'm from this company. I'll tell you learn Simulink. Okay. I mean, I can tell you there's nothing else which even competes with it out there. That's why all the industry is using this. So if you're a mechanical engineer, you should be learning Simulink, in my opinion. If you're learning Python, MATLAB will be very easy for you. It's almost similar syntax. Just go to this link, and in 5 or 6 hours, which is like, you can do it today if you want, you can learn the basics of both of these things. In my opinion, Simulink is what mechanical engineers should be learning. It's not a programming language, it's more like an environment, I'll show you.
Yes, sir. And how can we link FEA tools like ANSYS and flow analysis with MATLAB, sir?
You can go and check the documentation. So ANSYS, I think, already has some form of integration. I know COMSOL definitely does. All of these, if you're working with a well-known software package, they will typically have a MATLAB interface somewhere. And of course, you can always just export your data, and then you can have like a lookup table. So let's say from ANSYS, you have a table of deflection versus force. That is a two-dimensional table of data. You can just import that into MATLAB as an array, and then your Simulink model can read how much is the force, this much will be the deflection, or the other way around. So
Yes, sir.
all of these softwares will typically have links.
Yes, sir.
Okay. Let me show that questioner's question because it was quite a good one. So this is Simulink. You basically drag and drop blocks from the library browser into this interface. And if I go to Simscape, you have a bunch of libraries here. So we have in the foundation library, let's say we have a bunch of mechanical components. So these will include things like your angular velocity source, force source, torque, etc. You will also have spring, damper, mass, fixed surface, etc. So I think the question was about, was it about a damper?
Yes, sir. How can we import the springs and dampers?
Springs and dampers, yeah. Okay, so I'll start with a mass. I'll put in a spring and a damper. Okay, so let's say that my mass is here. It is connected with the spring and damper system. I mean, this is just how you draw diagrams in class also, right? And
Yes.
this is connected to some fixed surface at the bottom. Oops. Okay, so that is a suspension model. Now what we want to do is we want to put in maybe some force. So if the force is coming from the road, it will come down here. If it is on the body, it will come from up here in the network. So I go to mechanical sources and I'll put in an ideal force source. Maybe I'll put it from the bottom as if it is coming from the road side. No, actually this won't work. I'll have to put it here. This is because this part is connected to the ground, so you have to do a little bit of additional fiddling. I don't have time for that. And then you just use something like, let's say, sine wave block. So I take a sine wave and I convert it from a simulating signal to a physical signal. Sorry, I'm just trying to find the right block here. So I take some sinusoidal input, force, I feed it to this force block, and then maybe what I want to do is just get a measurement of how this mass is moving. So I'll get one of the sensors, maybe an ideal translational motion sensor. I'll connect it one side to the top, one side to the bottom. And then in the scope, I can see how my system is going to move. Let's see the position of this, and I'll put that in the scope. Okay, that's it. That is a virtual test rig for a suspension. You can change the force from down here. You can go into the damper, and you can change the damping coefficient from here. If you just double click on it, you can double click on your spring, and you can change the setting here. The code is all viewable. So if you click on source code, it will actually show you what code it is taking into account. So force equals spring rate times the displacement x. That's it. That's just the equation there. Let me put some displacement on this. Maybe displacement of 10 at a frequency of 1. And I'll run this for 100 seconds. Let's just see what happens. I've never built this before, so I have no idea what's going to happen. Oh, sorry, I forgot one block. You have to put a solver with this. So this solver tells you that it's an equation which has to be solved in a particular way. Okay, so I can now check that with this mass, with this damper, with this spring, this is the kind of displacement profile I'm going to get. So it's plus minus 0.01 meter, which is 1 centimeter deflection. Now I can go and make my damper stiffer. So I can make this 10 times harder. I can run the system again. And now it's a much smaller deflection. It's like 0.8 centimeters or even smaller. So like this, you can change various aspects of your system, and you can make very, very complex systems out of this. You can model a whole airplane or a whole car, and you can model everything about it. So once you develop the skill, it becomes much easier. So I hope that answers that question.
Yes, sir. It also answers the follow-up question like how we can input the parameters. There is one last question that where can we find some examples for electromechanical simulations in MathWorks?
Right. So if you just go to MATLAB and you type, let's say doc simscape. Doc stands for documentation. All this is publicly available as well on the internet. So this will open up the Simscape documentation. If I click on examples, you'll see there's almost like 100 examples, just under 100. So let me find some electromechanical system. So this is like a permanent magnet DC motor. On one side, there's an electrical circuit, which is in blue. On the other side, there's a mechanical circuit. Here is one with the thermal and electrical circuit. And we can find more probably down here. So here is like a solenoid with some magnetic blocks. So you're applying some voltage in this coil and it will generate some physical mechanical force. So you have electromechanical models. You have hydraulics. So that's connecting fluids and mechanical systems, etc. So there's a whole bunch of this. I mean, you just go to the documentation and see. Okay, I think I'm out of time. I don't want to eat into my next person's time. So.
Yes, sir. Yes, sir. All the questions have been answered. And now I would like to switch to Reynolds sir for a vote of thanks.
Thank you so much. Thanks.
Dhruv sir, really thank you. So we are really grateful, no, as you accepted our invitation and delivered your session in our workshop. I know how busy schedule you have, and really we thank you for taking out your time and coming and sharing your expertise with our students. So already, you have been to our campus and your team, they are really great. So we have taken us a journey into how R&D is done in the different firms. So it will be really a very good eye opener for all our students who are aspiring to join these firms and to take their career forward, to contribute their skills and their knowledge to the society. The case study of system design on electric vehicle. No, you have really extensively you have explained it. So the information, your presentation and the depth the depth of information that you gave us was really inspirational. So once again, the last 5 minutes, how dedicated you are, how sincere you are. You have shown us by immediately going to the software and developing the code and other thing. Once again, you have easily exceeded our expectations, sir. I can really tell you that. So, and regarding the curriculum coding, you have really suggested a very good thing. How mathematics is included in the curriculum and how coding has to be included in the curriculum. In VAT, our students are learning all the different codings. In fact, faculties, our own mechanical engineering faculties are handling sessions on Python, MATLAB, and everything. So we are into it, and we hope that our students take this workshop as a wonderful opportunity, as an eye opener, and they also involve themselves in coding, so that your session on system designing will be really helpful for them. Thank you, sir. Thank you for your wonderful session and your participation. And I asked the participants to join. Just I think only 10 minutes is left. I think the next speaker is ready. So we'll be starting the session by 5 p.m. Thank you, Dhruv sir.
Thank you very much, Reynolds sir. And I'll share a feedback form. So if anyone wants to reach out to me, I'll put my email address there. And if any faculty wants to reach out for curriculum, you can also fill that form. I'll get that.
You can just share your information in the chat box.
Thank you so much. Thanks. Have a nice afternoon, everyone.